So from the last lesson, we know that the area formula for finding the area of these regular polygons is not that complicated. But what can be more complicated is figuring out how tall that apothem is. And I'm going to show you how to use the Pythagorean Theorem or trigonometry Sohcahtoa to figure out that apothem length. The Pythagorean Theorem can be useful if you know some information. For example, if each of these sides is 10 units long, then this bottom thing can be split into a 5 and a 5. Since that apothem comes down to the midpoint, and since it's at a right angle, if we drew in what they call the radius of the pentagon, you can see that a nice right triangle is formed. Now, if you happen to know one of those other lengths, for example, the radius length, if I told you that was 8.5, then you would have enough information to find the apothem using the Pythagorean theorem. Now you can only use the Pythagorean theorem if you know two of the sides of that triangle and are just missing one of them. So that's where trigonometry comes in. What if you only knew that the side lengths were 10, so you only knew that length of 5? Well, I could give you a little bit more information if I told you that this upper angle right here was 36 degrees. Then that would be enough to figure out how big your apothem is. Because from that angle we would have the opposite side and the adjacent side, and we would be able to set up a tangent ratio. TOA, tangent of 36 degrees, equals opposite over adjacent, so 5 over a. And then you'll remember you could just cross multiply to find the length of that apothem. We're going to do 4 examples just to make sure that you are understanding this. One thing that's kind of neat about hexagons is that the radius length and the side length are always the same. So here's an example where I have a hexagon with side lengths of 10. And like I said, we would know that that splits this into a 5 and a 5. And that means on this little right triangle, there's the apothem, and I know 2 of the side lengths. And when I know 2 of the side lengths, I can use the Pythagorean theorem. Bonus points if you noticed that the short leg doubled makes the hypotenuse, which makes this one of those special triangles. Isn't this a 30, 60, 90 setup? So you could even skip the Pythagorean theorem and just write down 5 times the square root of 3 if you remember that stuff. That little trick really only works on hexagons, so in most cases you'll be stuck using the Pythagorean theorem. A squared plus b squared equals c squared. So we just found out that the apothem has a length of square root of 75, and I do not want you to round that, because we do not want to round until our final answer for the area. But once we have that apothem length, we are ready to throw it into 1/2 apothem times perimeter. And you're literally just going to write in that square root of 75 as your apothem. Our perimeter, each side is 10, and there's 6 sides, so a perimeter would be 60. And now I just want you to type that in as the square root of 75. So we're going to take 1/2 times the square root of 75 times 60. And I'll round that to 2 decimal places, I think. 259.81. That's area, so square units. We'll try another one just to make sure you've got this. We actually know the length of the apothem this time. They're telling us that the apothem is 7 units long. But what we don't know is how long are the sides of this heptagon. Luckily, they did give us a radius. So we'll be able to use that Pythagorean theorem to find out this side of the triangle. A squared plus b squared equals c squared. And again, I don't want you to round that. B is going to be the square root of 11.84. But what does that tell us about the length of each side? Remember that this b length is only half of the side length. So each side is actually going to be 2 times the square root of 11.84, which if you type it in is about 6.88, but I don't want you to use that number. I want you to use this exact value up until our final area answer. So again, this time we did know the apothem, but the perimeter, what's the perimeter going to be? Well, we'd have to take 7 of those side lengths, right? So 7 times 2 square root of 1.84, 7 times 2 is 14. So our perimeter is going to be 14 square roots of 11.84. Is that awkward? Yes, but we are going to get a nice precise answer then because we haven't rounded anything until this final answer, which comes out to 2 decimal places, 168.61 square units. So we can only use that Pythagorean theorem if we know 2 of the sides of the little right triangle. You'll notice on this one, to find the apothem, I would be able to say that this little side is 15, but this time they didn't tell me how long the radius is. So I actually don't have enough numbers to Pythagorean theorem. So what do? I'm going to have to use Sohcahtoa. I know what you're thinking. They didn't give me any angles. Well, I have a trick for that too. You know how if we look at this central angle, the total degrees around here would be 360 degrees, right? A full circle has 360 degrees. Well, how many triangles does an octagon get split into? 8 triangles, right? So if we take that 360 and we split that into 8 equal pieces, that's 45 degrees for each triangle. So each of these is a little 45-degree angle. I skipped that bottom one because I actually want to split that bottom 45 degrees into 2 angles, right? So take that 45 and split it again, and we're going to get 22.5, which is that little angle that's in our right triangle. That's kind of hard to see, so why don't we draw it out separately? We're looking for the apothem. We know that this bottom leg is 15 on our right triangle, and this top angle is 22.5 degrees. So how can I find that apothem? Well, from the 22.5 degree angle, I have the opposite, and I wish I had the adjacent. So that's a toa. I'll be able to do a tangent. Tangent of 22.5 degrees equals opposite over adjacent, and that adjacent is the apothem. If we cross multiply, we're going to take the a times the tangent of 22.5 equals the 1 times the 15. So this is one of those where when we solve for a, we're going to wind up taking the 15 divided by the tangent of 22.5. And yeah, that comes out to be about 36.21 for that apothem. But again, I don't want you to round that yet. We are going to use literally this for our apothem and not round anything until our final answer. But I'd say we're ready for 1/2 apothem times perimeter, right? That apothem length seems a little clunky, but it's nice and exact. And how about the perimeter? It's an octagon with side lengths of 30, so 8 30s would be 240. Now we get to type all of that in at once. You should probably try this. 1/2 times 15 divided by tangent 22.5 times 240, all in one line of your calculator. Now it's okay to round because this is our final answer. 4,345.58 square units. We probably need to do one more of those, huh? Here's another example where they gave us the apothem, but we have no idea how long the sides of the pentagon are. So let's investigate our favorite little right triangle here. Again, I can't use the Pythagorean theorem unless I had another number maybe here, but I'd like to know this length so I can figure out how long the side of the pentagon is. But I also don't have any angles. How do we fix that? Remember that this inner circle is 360 degrees total. How many triangles does a pentagon get split into? 5 sides, 5 triangles. So I can take that inner circle of 360 and split it equally into 5 pieces, and that's 72 degrees each. Again, I didn't fill in that bottom one because I actually want to split the 72 in half again. 72 split would be 36 degrees. So a little 36-degree angle in our right triangle. Again, I'm just going to pop that out so that we can concentrate a little better. We know that apothem is 12. We're looking for this side length of B, and that top angle is 36 degrees. So this time, since we're up at the 36-degree angle, we're looking for the opposite, and we know the apothem, the adjacent side. So this is another tangent, a toa. Tangent of 36 degrees equals opposite over adjacent, B over 12. And this is the type that solves a little bit easier when we cross multiply. Tangent 36 times 12. I like to write it 12 times tangent 36 equals b times 1. And I know it's tempting, but we're going to leave this as the exact answer until we're ready to round our final area. Now, if you want to check that out, type it in. It's about 8.72. That maybe is a smart move just so you can see if it makes sense on the picture. Make sure you did your Sohcahtoa right. And once we know that length, we can go to that area formula. The area is 1/2 apothem times perimeter. This time they gave us that nice apothem of 12, and the perimeter is going to be the awkward one. If the length of B is 12 tangent 36, then the length of this whole side would just be double that, right? So if you double 12 tangent 36, you get 24 tangent 36, and that's going to be the length of each side of the pentagon, which is pretty awkward but very precise. Back to our formula, 1/2 apothem times perimeter. We just need that perimeter now. How do we find the perimeter of a pentagon? We would just take each side length and add it together, or we would take 5 times the length of the side. So we've got 5 of those 24 tangent 36s. And if you'd like, you can actually multiply the 5 times the 24. That's 120 tangent 36 for the total perimeter, which is just over 87 units, but we don't want to round that yet. So we're going to use 120 tangent 36 as the perimeter. Now it's time. Now we're finally going to use our calculator to type all of that in one line. 1/2 times 12 times 120 times tangent 36, and that is coming out to 523.11 square units. And that's as precise as we could have done it because we saved that rounding until the very last step. So every problem you do today, you're going to either use the Pythagorean Theorem, maybe you know 2 sides of that little key triangle, or you'll use Sohcahtoa, trigonometry. That happens when you only know one of the sides, but then you have to do that extra calculation to find that central angle.